Hi everybody. Tonight we're going to talk about lovastatin. Lovastatin is a cholesterol-lowering agent under the group of drugs characterized as statins. It is isolated from a strain of Aspergillus terris. Lovastatin is an inactive lactone which is hydrolyzed to the corresponding beta-hydroxy acid form. Lovastatin serves as an inhibitor of 3-hydroxy-3-methylglutarol coenzyme A, HMG-CoA reductase. HMG-CoA is a catalyst for the conversion of HMG-CoA to mevanolate, an important rate-limiting process for the cholesterol biosynthesis. The empirical formula of lovastatin is C24H36O5. Lovastatin's molecular weight is 404.55 grams per mole. Lovastatin reduces both normal and elevated LDL cholesterol concentrations. This includes the reduction of serum cholesterol. Lovastatin may not only reduce the production of LDL cholesterol, but also induces the LDL receptors. This LDL receptor induction effect undoubtedly benefits the PF patient who suffers from the genetic disease which results in dysfunctional LDL receptors. Evidence also has shown that lovastatin not only causes the reduction of cholesterol, but also reduces the circulating LDL particles. Lovastatin can also increase HDL levels and reduces VLDL cholesterol and plasma triglycerides. After an oral dose of lovastatin, it is readily hydrolyzed to the corresponding beta-hydroxy acid, lovastatin, and its beta-hydroxy acids are highly bound to human plasma proteins. The plasma concentrations of the drug peak after 2 hours and decline to 10% of peak in 24 hours. Lovastatin has high selectivity for the liver, its primary site of action. Lovastatin has been shown to be highly effective in reducing total cholesterol and LDL cholesterol in heterozygous familial hypocholesterolemia patients. It is interesting to note that the dosage given in the evening is more effective than the dosage given in the morning. This might be because cholesterol is synthesized mainly at night. It is even more interesting to note that patients treated with lovastatin had shown side effects of shorter sleeping hours. Lovastatin also shows significant effect on coronary atherosclerosis. Since lovastatin inhibits HMG-CoA reductase, which is a catalyst to HMG-CoA in cholesterol biosynthesis, it is reasonable to hypothesize that the two molecules, HMG-CoA and lovastatin, share some common structural features. This is the site of the terminal carboxylic acid group of the hydrolyzed beta-hydroxy acid will form. Following an oral dosage, a water molecule does a nucleophilic attack on the carbonyl carbon of the drug and opens the ring, resulting in the beta-hydroxy acid form of lovastatin. This is a picture, if you can see it. This is a picture of the beta-hydroxy acid form of lovastatin. The lactone group seen in the lovastatin picture shown in the lovastatin picture is hydrolyzed and open to form the terminal carboxylic acid group on the beta-hydroxy acid. The CoA diester group of CMG-CoA is reduced to an alcohol by CMG-CoA reductase in an NADPH-dependent reduction to form mevalonate in the isopentyl pyrophosphate formation process. The group that is similar in property to the thiester group on HMG-CoA is the newly formed terminal carboxylic acid group. Since lovastatin is inactive in its lactone form, it is reasonable to suggest that HMG-CoA reductase will reduce the beta-hydroxy acid at its carboxylic acid end in the similar fashion to the thiester reduction. Research has suggested that HMG-CoA group binds to the active site of the reductase, HMG-CoA reductase, with NADH as the other cofactor. HMG-CoA is bound predominantly by the large domain of one monomer and NADH by the small domain of the symmetry-related monomer. This picture is one of the monomers of the HMG-CoA reductase. Right there. The arrows point at the active sites on the junction of the top end of the stem of the T-shaped monomer. These active sites are the large and small domains on the dimer. The HMG-CoA is bound by the large domain in an extended form that stretches across the active site cavity. The NADH is bound to the small domain of the symmetry-related monomer of HMG-CoA reductase. In these binding configurations, the nicotinamide ring of the NADH is positioned within 3 angstrom adjacent to the scissile bond of HMG-CoA. Thus, dimerization is a prerequisite for the active sites in HMG-CoA reductase. This reaction is analogous to the two successive reactions of an aldehyde hydrogenase and an alcohol hydrogenase, but both are done by HMG-CoA reductase. A competitive inhibitor acts by reducing the concentration of free enzyme available for substrate binding and reduces the amount of product. In this particular case, lovastatin, in its beta-hydroxy acid form, acts as a competitive inhibitor and reduces the binding of HMG-CoA to HMG-CoA reductase, thus reduces the amount of cholesterol product. The suggested hypothesis is that the structure of lovastatin has the ability to bind to HMG-CoA reductase large domain in a way similar to that of HMG-CoA. Also, instead of the thiester group of HMG-CoA, binding next to NADH it is the terminal carboxylic acid group on the beta-hydroxy acid that will interact with the NADH in its competitive inhibiting process.